First of all, what is factoring? Factoring is the process of breaking something down into its smaller parts. 6, for example, can be broken down multiplicatively to 2 and 3. Both 2 and 3 are prime, which means they can't be made up of smaller parts. But what about something like 3x squared plus 4x minus 4? What could multiply to make that? Or is it prime, meaning it's as small as it gets? Before we get into the process of taking things apart, let's look at how they're put together. We'll start with addition. What does 3 plus 4 look like? In elementary school, you might have seen 3 things and then 4 more. We'll line these up and notice we have 7 in a row. This doesn't just work for counting discrete things, it extends to measurement too, where you can have decimals, fractions, and irrational numbers. If you take a segment of 3 inches and then extend it by 4 inches, you'll end up with a segment 7 inches long. So addition is just extending something in a line. But what about multiplication? Going back to elementary school again, 3 times 4 means you have 3 groups of 4 things. We added dimension to this, and rather than extending the line, we put one row underneath another. We end up with an array that has 3 rows of 4 for a total of 12 objects. This too can be extended past counting and into measurement, and we can think of multiplication as the creation of a rectangle. The area of a rectangle is the result of basic multiplication, length times width. Let's extend these properties. We're going to think of this product as a rectangle. One side is x squared plus 2x plus 3. I'll show the addition by thinking of each term as a separate piece of the segment. The other side is x squared minus 4x plus 5, again broken up between terms. Extending these segment breaks creates, in this case, 9 smaller rectangles, but the length and width of each are clearly marked, and the areas are simply the product of these single terms. X squared times x squared is x to the 4th, x squared times 4x is 4x to the 3rd, etc. The area of this rectangle is the sum of the areas of the smaller rectangles. When arranged in a grid like this, patterns emerge. All of the x to the 4th terms are along this diagonal. This diagonal has all the x to the 3rd terms. X squareds are here, and x to the 1sts are here, and the terms without x's are here. Adding along each diagonal, we get x to the 4th minus 2x to the 3rd plus 0x squared minus 2x plus 15. We'll do one more example of this. The width is x plus 4, the length is 2x plus 3. Break it right before any addition or subtraction. X times 2x, 2x squared, x times 3, 3x, 2x times 4 is 8x, and 4 times 3 is 12. But what if we wanted to reverse engineer? What if we wanted to know how 2x squared plus 11x plus 12 breaks down? Well, we know in this first diagonal is all of the x squareds, so that's 2x squared, and then somehow these two add up to be 11x. And this one is all of our no x's, x to the first, or 0, so that's just plus 12. Now here's the funny thing about these. These diagonals will multiply to be the exact same thing, and you can check that out here. If we multiply this diagonal, we get ABCD. If we multiply this diagonal, we get ABCD. So this diagonal multiplies to be 24x squared. We know they have to add up to x, so these have to be both x's, so we can kind of ignore the variable here. We're looking for things that multiply to be 24 that add up to be 11. If you can't guess it right away, just start making pairs. 1 and 24. And the next number of 5 doesn't go in, so 6, and we're back at this side of the list. So these are the only 4 pairs that will multiply to be positive 24. They could both be negatives, but they're not because they need to add up to a positive number. 1 plus 24 doesn't work. 2 plus 12 doesn't work. 3 plus 8 works. That's the 11 that we're looking for. So one of them is 3 and one of them is 8, and it does not matter which is which. What we're going to look for now is the greatest common factor of this top row, because this number here multiplied through there. So There's no numbers in common other than a 1, but there is an x in common. And then we just say what times x gives us 2x squared? Well, that's a 2x. What times x gives us 3x? That's just a 3. What times 2x gives us 8x? That's a positive 4. And just to check, 4 times 3 equals 12. Yep, there you go. So the factors of this are x plus 4 going down the side and 2x plus 3 going across the top. And that's how to use the area model to factor a trinomial. You'll notice that the 4 things that go into the smaller rectangles here are the exact 4 things that went in when we multiplied together. So this really is a reversal of the process. Let's do one more for good measure. Our x squareds are going to go here, x is here, and then no numbers here. So that's 3x squared, and that's a negative 4. And these two somehow add up to be 4x, but we don't quite know how yet. Multiply this diagonal, we get negative 12. I'm going to ignore the x squared, but we know that's there, but we already have the x's here, so we don't need to deal with that. So 1 and 12, 2 and 6, 3 and 4. And then 4, so we're back at these are the only 3 pairs. But notice they need to multiply to be negative 12, so one of these has to be negative. They add up to be a positive number, and the way to add up to be a positive and multiply to be a negative is you need that one of them has to be negative, but the bigger one is positive, or else the result would be negative. So this would be the side that would have to be the negative number. We can check here, negative 1 plus 12 is 11. And this is it. So the magic numbers we're looking for are negative 2 and positive 6. Now we're looking for the greatest common factor of this top row. They do have a 3 in common as a factor, but also an x. What times 3x gives you 3x squared? X. What times 3x gives you plus 6x? Plus 2. What times x gives you negative 2x minus 2. And then this last box is our check. Negative 2 times positive 2 does equal negative 4. So the factors of this trinomial are 3x minus 2 and x plus 2. Thanks for watching.